In general physics, we learn about the simple pendulum as an example of simple harmonic motion. Here, although the equation of motion contains the term sine theta, we estimate it to theta for easy analysis. Then how can we analyze the pendulum motion more accurately without estimation? Applying the elementary techniques, we get an integral very difficult to find. Now, we realize that lowering the order of the equation is necessary. We try using the conservation of mechanical energy to find the angular velocity omega as an equation of theta. We will first analyze the first half period of pendulum, and then use symmetry for generalized formula. Then we get the following integral. In order to evaluate it, we first need to learn about elliptic integral. Suppose we must find the arc length of an ellipse from argument 0 to theta. Writing the equation of ellipse in polar form and integrating gives the algebraic form of the length, which is defined as the first kind of elliptic integral, or f theta, e. We first change the cosines in the denominator to squared sines. Then we perform appropriate substitution, which changes t to difference of two elliptic integrals. We acquire the period by substituting 0 to theta and multiplying 4. Defining the corresponding time tau, we get the formula that expresses theta as a function of tau. We can contemplate this result in two ways, one algebraic and the other geometric. Let's start with algebraic consideration. Using the generalized binomial theorem, we can express f pi over 2 k in a form of series. Using integration by parts, we can calculate the integrals, leading to the final form of the series. Thus, we can also find the period of pendulum. From this formula, we can realize that estimating sine theta to theta was equivalent to ignoring all terms except or equals 0. Furthermore, we find out that the series term expresses the ratio between periods of actual oscillation and small oscillation. The period extends as amplitude increases. In particular, the period is 1.18 times longer than small oscillation when the amplitude is 90 degrees. Now, let's interpret the formula geometrically. We used the same substitution as in deriving the formula, in order to define the phase of pendulum. Because the rate of change of the arc length is always plus minus square root g over L, we can form an elliptic model of a point moving back and forth at a constant linear speed, where the phase is the angle measured from the semi-minor axis to the point. Using this model, we find intuitively that the period is the perimeter of ellipse divided by the linear speed of the point, which gives the same result as the original formula. When the amplitude is small, the ellipse turns to a circle, which is exactly the model we use to express the simple harmonic motion. To summarize, we did a formal analysis of pendulum motion using the elliptic integral and contemplated it in two ways. While the algebraic consideration gave us a mathematical form of the period, the geometric consideration let us develop an intuitive model of the motion. It is clear that both interpretations show the close relationship between algebra, calculus, geometry, and physics. Especially the geometrical analysis also show that we can measure the perimeter of an ellipse without calculus or even drawing the curve, we can just measure the period of pendulum. And that was an introduction to my research about the pendulum motion.